Okay, so for this section that we started working since last time, well, that's again a continuation of what we did basically at the end of chapter 4 on antiderivatives. So for antiderivatives, what did we did again? It's to basically look at the inverse operation of the derivative. I mean that and that prefix anti, that's what it denotes. You know, to do the opposite of it. And well, back in that section or at the end of that chapter, we were looking at what function has a derivative of, well, this function right here, right? That was what the antiderivative was. Then we introduced some formulas to find antiderivatives. So in order to help us find those antiderivatives by using a more systematic way, a more formulated way, rather than trying to guess, which could be a little weird to do. All right, but then we describe that antiderivative as a new operation called the integral. And in this case, the integral, which is based on finding the antiderivative, we put that together with its geometric interpretation, which, by the way, that's to find the area under the curve within the limits a and b, within an interval, right? So we will use this idea of finding integrals later well, pretty much the whole semester in Calc 2. And well, later in Calc 3, you will look at this kind of double and triple integrals over other kinds of regions, not just like an interval, but rather over a surface, over a solid, over a path. It's gonna be a lot of ways to describe this kind of integrals and other interpretations, but essentially it has to do with finding areas, if we will. But the simplest case is the single integral that we're looking right now in single variable calculus. Well, so but the idea right now is to get familiar with the tools to find antiderivatives, and in particular, we're going to look at the easiest cases. You know, this table we discussed last time, it's a very, very small table of integrals. It's the same formulas as the antiderivatives. However, now we introduce the integral symbol and the differential symbol. There's a few typos here that I would like to fix. There are some u's that shouldn't have been there. This should have been an X, and I think that was about it. I already fixed one over here last time as well. All right, so we did a few examples. Again, it was essentially the same, but I took my time to show you every single step, what we do essentially. Well, for this class, it would be great if you write every single step right here on a quiz or an exam. That way, if something doesn't compute in the end, something doesn't check, you have everything pretty much so you can see where the source of the mistake is. However, as we move on through these topics, you will be getting fluent on this, and especially when you get to calculus 2, you will be as well very fluent on this, and you will be able to pretty much go from original example to final answer in one shot. But well, that's not my expectation right now in this first course, in this introductory course of integrals. Well, that will be, but you'll see how this is going to become a second nature back when you get to calculus 2. All right. Well, in the meantime, let's keep working on more integrals. Well, we evaluated a few indefinite integrals, and we evaluated, I believe there's or two definite integrals. We did two definite integrals. All right. So again, for example number 2, this is what we're going to do. They're asking us to verify this statement. Okay. So this means what they're asking us to show is that indeed this is the integral of this function. In other words, if this is little f, this is big F. All right? And for both examples A and B, don't even attempt to perform the integration, because up to this point you guys don't have the necessary tools to do these integrals right here. Unless, again, you have taken a calculus course, either you took this same class before or you took a calculus course back in high school. Maybe you learn how to integrate ln of x. Well, that's a more advanced method that we covered in calculus 2. It's called the integration by parts method. In this case, well, we have a differentiation rule for ln of x, but we don't have an integral rule for ln x. Nevertheless, we have an integration rule that yields an ln x, but the integral of ln x, you don't know how that works. That again, we're going to learn it in Calc 2. So how are we going to verify each statement? Essentially, what we're going to do is to set this big F of x as our x squared plus 1 plus c. So we're going to verify this by differentiation, because if you integrate this and you get that, then take the derivative of this and you should get this back again. All right? So, but I would like to rewrite this function in radical form. Instead, I'm going to write it as a rational power. And well, so big F prime, it's going to be 1/2 x squared plus 1 to the negative 1/2, and the derivative of c, because c, it's just a constant. The derivative of a constant is 0, which doesn't show in the integrand if you notice here. Well, so, but in this case, I need to do a mini chain rule. I need to differentiate the inside of the parentheses. And, well, that's going to be a 2x. And in this case, you can see how these 2's get canceled. And I'm going to write this as x over this quantity with positive exponent. And this is big F prime. That's x over the square root of x squared plus 1, which actually indeed matches what we have in the integrand. So in this case, what we're trying to verify is that this integral was done correctly. Well, in this case, again, we require the method of substitution, which we don't know yet, but we will know it on Friday. We'll start working on substitution on Friday for sure. All right, so letter B, the integral of ln of x dx equals x ln x minus x. Again, they want us to verify that the integration was done correctly. And again, let me note this. This will be done in Calc 2. So we're not going to finish this course with the necessary tools to integrate ln of x. We'll learn that in Calculus 2. You'll see. So again, let's set this as our big F. This is essentially our little f. And our little f is essentially the derivative of big F. Of big F, I mean. So big F equals x ln x minus x plus c. Let's take the derivative. And to take the derivative of this function, well, notice the product between x and ln x. We need the product rule, which it would be a good idea to recall what it is. That is u times v prime. That's u prime v plus v prime u. So that's the product rule. So so that's what, okay, the derivative, so big F prime, that equals x, the derivative of x, which is 1 times ln x, plus the derivative of v, which is ln x. The derivative of ln x is 1 over x times x, minus the derivative of x, and in this case that's a negative 1. And the derivative of plus c, which is just a constant. Well, the derivative of a constant is 0. So we don't need to write anything. So let's simplify this. Let's clean this up. So we can divide out these two x's. That's going to leave us with big F prime. That's going to be 1 times ln x. That's ln of x. Plus 1 minus 1. Cancel these ones. Big F of x equals to ln of x. All right? And indeed, check how this actually matches the integrand in the original problem. But again, this is something that we will do. How to integrate this ln of x? That's Calc 2. It's called the method of integration by parts, which is essentially the backwards way to go about the product rule of differentiation. In fact, it's based. It comes from the differentiation of a product of two functions. All right. So what else do we have? So we have more integrals right here. Evaluate each indefinite integral. However, notice how these functions are a little weird. In fact, we cannot just integrate these functions just yet. Be careful. One thing I would like to point out is that this is not the integral of x plus 4 dx times the integral of 2x plus 1 dx. So don't do that. There's no such thing as a product rule for integration in the same way that there is a product rule and a quotient rule for integration. Don't do this. All right? Instead, in many situations, we need to do some algebra, some preliminary work before we can actually integrate terms, because we cannot just integrate factors like this. We integrate terms. So what we're going to do in this case is use the distributive property or FOIL. So that's going to be the integral of x times 2x, that's 2x squared. X times 1, that's x. 4 times 2x, that's an 8x. And 4 times 1, that equals to 4 with respect to x. So that's all FOIL. That's all FOIL. Let's actually combine like terms. And we'll notice how we can combine x with 8x. That's going to leave us with, that's a 2x plus 7x. 9x actually. There was a negative. Plus 4. And well, again, my advice is to write it as one single integral for every single term. I know if at this point you already feel comfortable with just integrating every single term in your head, that's fine. Just make sure that you know what you're doing when it comes to a quiz or an exam. Mm-hmm. Which one? Oh, x squared. Mm-hmm. Yeah. Just make sure that you know what you're doing. But in the meantime, again, personal advice is write this as two integrals. 2 times the integral of x squared dx plus 9 times the integral of x dx plus 4 times the integral of dx. And over here we are going to use the general power rule, because in this case we're integrating x's. How about we write down that formula again? So the integral of x to the n dx equals x to the n plus 1 over n plus 1 plus c, and in this case with the condition that n is not negative 1. Whenever n is negative 1 for the general power rule, we'll have another rule, and we already discussed this last time. And actually I did the example, because if you do negative 1 plus 1, well, in the numerator a power of 0 is totally fine. However, the issue here is the negative 1 plus 1 in the denominator, which deals and a 0 in the denominator, which is where things come a little weird. We get some undefined quantity, and well, we're not going to do such a thing. All right? So that's 2 times x to the, I'm going to do the 2 plus 1 over 2 plus 1 plus 9 x to the, essentially there's an invisible 1 plus 1 over 1 plus 1, and plus 4 times the integral of dx. Well, that's one of the properties. Let me see if I have that property here at the top. I believe I do. Yes. Well, no, not really. But in this case, the integral of dx, it's going to be simply x times 4 in this case. So, quick side trip here. When you have the integral of dx, which happens to be x plus c, so you can think of this essentially you can think of the integral canceling the derivative, because these two are essentially opposite, opposite operations. In the same way that we have like e to the ln of x, these two cancel out to give us an x, and ln of e to the x equals, cancel this out, so essentially the integral symbol cancels out the differential symbol, because again these two are opposite operations. All right, and well, let's add the plus c. Don't forget the plus c, because we're dealing with an indefinite integral. And well, that's going to be 2 x cubed over 3 plus 9 x squared over 2 plus 4x and plus c. Okay, final answer. Letter B. Let's do another one for letter B. Well, in this situation for letter B, well, we cannot integrate a quotient. So again, just the same way I showed you earlier with a previous example, this is not equal to the integral of 1 plus the cube root of x plus x dx over the integral of x dx. No, this is not what we're supposed to do. There's no such thing as a quotient rule for integrals, all right? And well, instead what we're going to do, we're going to split this up into 1, 2, 3 terms and divide those 3 terms by n. However, before doing that division, it would be better if we first write this radical in terms of a rational exponent. That is, the integral of 1 plus x to the 1/3, and again, the index of the radical is the denominator of the rational exponent, and the numerator, which is a 1 that comes from the power of x, which is an invisible 1 in there, okay? And that's plus x, and divide that by x dx. And well, then the property that we're going to use is to split up the quotient. Essentially, it all stems from the following property. That is, a plus b over c. You can divide a over c plus b over c. And this can be extended to more terms. Like in this case, we have 3 terms. Now, careful. This is okay. But this one, is not okay. And this is a very common mistake in algebra. And this is the kind of mistake that you don't want to do in calculus as well. For example, when like integrating the function that we had over here, let me take it back. This is not equal to the integral of 3 over x squared plus 3 over 1. I've seen this many times. This is not correct. This is not how we split up terms. So I wanted to point this out so you're aware of this, and don't do this on a quiz or on an exam or even in the homework. You're doing the homework and it's not coming right. Well, that's because we are using incorrect algebraic techniques right here. All right. Okay, let me get rid of this because I'm going to need more space. Anyway, it's going to be recorded and it's going to be there. All right. So, well, let's split it up. That's the integral from 1 over x plus x to the 1/3 over x plus x over x with respect x. And well, 1 over x is simply 1 over x. And well, in this case, we would need to subtract the powers, because we have the same base. We have a division of them. What we do is subtract the powers. So 1/3 minus 1, that's going to give us x to the negative 2/3. And x over x, that's simply 1 dx. And again, just split it into three separate integrals and integrate each individually. So that's the integral of 1 over x dx plus the integral of x to the negative 2/3 dx plus the integral of dx. Well, again, let's see if we recall some of the properties. Okay, anyone? Any ideas for the first integral, the integral of 1 over x? What's that? What is that? Natural log, all right? Natural log of just x? Absolute value of x, all right? Recall that in this case we need to make sure that when we integrate the function 1 over x, whose domain is a set of all real numbers except 0, the domain of its integral, which is ln, well, that's essentially only positive numbers, but in order to keep the domain from the function that it's coming from, we need to put those absolute value bars to make sure that we include those negatives as well. And then in this case, plus x to the negative 2/3 plus 1 over negative 2/3 plus 1. And that equals to, oh wait, no. We're not done yet. So the integral of dx, again, essentially these two operators cancel each other. That's a plus x and then plus c. So all we need is to add those fractions. Well, 1 minus 2/3, which is essentially 3/3 minus 2/3, that's a 1/3. And plus x to the 1/3. Wait, hold on. No, never, yeah, that's fine. 1/3 over 1/3 plus x plus c. And well, we're essentially done except for the second term. How about we write that division by a fraction as a multiplication by its reciprocal, and this rational power will take it back to its radical form. So that's ln of absolute value of x plus 3 times the cube root of x plus x plus c. And we're done with this integral. All right. Again, it's the same rules that we're using, that we have been using since we first introduced the antiderivatives at the end of chapter 4. The same as the indefinite integrals and how we put it together with finding the area, except that now we are using the integral symbol and the differential symbol. So we're going to do another example. It's very similar, in which we will have to first split this up and then do the integration. However, this time we're going to have limits of integration for which we are going to use the fundamental theorem of calculus. And again, from the beginning of the section which we discussed last time, recall that the indefinite integral, the result of doing the indefinite integral, it's a new function, while the result of doing a definite integral, that is an integral containing limits, it's just a number, and that value that we obtained represents the area under the curve for this function within the limits 1 and 9. All right, so let's go ahead and do this integral. So number one, before even attempting the integration, let's do some algebra. So that's the integral from 1 to 9. That's 2t squared over t squared plus t squared root of t over t squared minus 1 over t squared. And well, even though I typed a dx, that's a typo. That should have been a dt, because that differential has to have the same variable as the variable in the integrand right here. All right, so that's a dt. Okay, so this one is going to simplify really nicely. Cancel the t squares here, cancel the t squares here. There's nothing to cancel in the third term. So in this case, well, we will be left with the following. So that's the integral of 2 plus the square root of t plus 1, or rather minus 1 over t squared. So that's what we're going to be left with, and that from 1 to 9. Now, we cannot integrate this just yet. Number one, I'm worried about the radical right here. We cannot integrate the radical just in one shot. And we cannot integrate the t squared while it's in the denominator. We need to make sure that this variable term, the t squared in the denominator, it's actually in the numerator. And of course, we can do that by just changing the sign of its power into the opposite sign, that is into negative sign. So let's go ahead and do that. That's the integral from 1 to 9 of 2 plus t to the 1/2 minus t to the negative 2 dt. Okay? And well, let's write this in terms of a few integrals. That is the 2 times the integral of dt plus the integral of t to the 1/2 dt and minus the integral of t to the negative 2 dt. Again, recall that the integral symbol and the differential symbol, they all go together. So a very common mistake I see on exams, on quizzes, is to just write this. No, make sure to write the whole thing, not just the integrand, but also to say with respect which variable you're integrating to. So, and well, the integral of the let's write down the limits all the way from 1 to 9 for the 3 integrals. And let's find the antiderivative or integral. Either way, recall that these words are interchangeable depending on the sources you use. I mean, like in the textbook or other resources online, they use different ways to say this, the integral or finding the integral or finding the antiderivative, or even there's another one, finding the primitive. That's another way to, so if you read the primitive, they're referring to the same thing, finding the integral. All right, so that's the 2 times t plus t to the 1/2 plus 1 over 1/2 plus 1 minus t to the negative 2 plus 1 and t to the negative 2 over negative 2 plus 1. And in this case, we can just use one single bar to evaluate this from 1 to 9. Okay? Before evaluating this, how about we do some simplification over here? So number 1, so that's 2t plus t to the 3/2 over 3/2 minus t to the negative 1 over negative 1. And be careful here with too many negatives going on. So number 1, okay, between 1 and 9, this negative right here, let me highlight them. This negative, with that negative, essentially we have a product that turns into a positive, and at the same time, I'm going to change this denominator, this division of a fraction, I'm going to change it into a multiplication by the reciprocal. So that's a 2t plus 2/3. Okay, and I'm also going to use a property of radicals. Well, what property of radicals am I talking about? Well, number 1, let me make some room over here first. So there is this property of radicals and rational exponents, that one that tells us whenever we have x to the m over n, so we have the nth root of x to the m power. Again, the denominator of the rational exponent is the index of the radical, and we get this as a result. M, which is the numerator of the rational exponent, is the power of the variable inside of the radical. However, there is a second version of this, and the other version is the n root of x and the whole thing being raised to the m power. So, and I'm going to use this version because it's going to be very convenient. The reason why it's very convenient is because in this case we will essentially evaluate the square root of x, the whole thing cubed. And if you observe these limits of integration, 1 and 9, they are both perfect squares. So it would be easier and even more efficient to compute the square root of the perfect squared, and then cube, and then do the other operation we require. Otherwise, when it comes to not being perfect squares, you might want to use the other version and just play with the powers and take out perfect squares whenever possible. I think we have done some of those before, but it's not the case this time. So minus minus, that's a plus 1 over t, and actually this is a t, not an x, right? And still from 1 to 9. It's time to evaluate upper limit minus lower limit. So 2 times 9 plus 2/3 square root of 9 cubed plus 1 over 9. So that's evaluating at the upper limit, evaluating at minus evaluating at the lower limit. That's 2 times 1 plus 2/3 of square root of 1 cubed plus 1 over 1. So that's the evaluation, that's the setup for the evaluation. Let's just simplify this using arithmetics, of course. Okay, so 2 times 9, that's 18. Well, this quantity, this second quantity, that's the one that's going to take a good minute to go. Well, number one, let's do one thing at a time. Okay, so the square root of 9, which is 3, that 3 getting cubed, it's 27. But that 27 divided by 3 is going to be a 9. And multiplied by 2, that's another 18. So that's another 18 right here. And plus 1/9. And then minus, in this case, that's a 2. And square root of 1 is 1. 1 cubed is 1 times 2/3. That's plus 2/3. And plus 1. So let's simplify 18 plus 18. That's 36 plus 1/9. And then 2 plus 1, which is 3, but minus in the front. That's minus 3, or rather, let me do 3 plus 2/3. And let's get the sign. 36 minus 3. I'm going to put the integers with the integers and the fractions with the fractions to make this a lot easier. Minus 1/9, or rather plus 1/9 minus 2/3. 36 minus 3, that's going to be 33. And well, here I would need to find LCDs to get the denominators the same. So I'm going to multiply numerator and denominator by 3, so we get a common denominator of 9. So that's going to be 1 minus 2 times 3, which is 6. 1 minus 6, that's negative 5. Negative 5 over 9. Well, to simplify this, I mean, you can use your calculator or just go 33 times 9. 7 carry 2, 9 times 3, that's 27, that's 29, 297, and then minus 5, that's 292. So this is 292 over 9. And that's final answer for this integral. And again, this numerical result that we obtain of integrating this madness, it's the value of the area under the curve for the function that we had in the integrand within the limits 1 and 9. All right. Okay, so this is a little bit more on integration. The next topic, which is the net change theorem. I think I would rather cover that next time because, well, there's a lot that we need to talk about it. I mean, in terms of application.